Good morning, student. In this class, we are going to discuss the formation of standing wave on string. Okay, this is a very common phenomena, and you can do this experiment anywhere. Just that you need a string and fix the both end of the string. Okay, and let's start our discussion on the formation of standing wave. In the last part of the video, I have told you that the standing waves are formed when the incident wave and the reflected wave superimpose, having a phase difference of pi or 180 degree between them. Okay. In order to form the standing wave, both ends of the string should be tightly fixed. That means when z is equal to infinity, z2 is equal to infinity, then only we can have the formation of standing wave, as I have discussed in the last class. Okay, so for that, the two ends of the string should be tightly fixed. Both ends should be fixed. No end should be free. Okay, and if we continuously vibrate one part of the string using an oscillator, that oscillator may be your hand or other kind of mechanical device, it doesn't matter, then we can see the formation of standing wave pattern on the string. Okay, now what do you mean by the standing wave? Okay, so let me discuss briefly what we mean by the standing wave. Standing means the position of the maxima or minima of the string will not change with time. Okay, that is the one of the characteristics of the standing wave. Okay, suppose when both end of the string is fixed, we have a incident wave like this. This is suppose incident wave. Okay, incident wave is moving in this direction, incident wave, and there will be a reflected wave if this end of the string is tightly fixed, and the reflected wave will be 180 degree phase shifted. So basically it will be in this fashion, as you can see. So this is 180 degree phase shift wave. Okay, so the reflected wave will be traveling along this direction, reflected wave. Okay, so when we continuously excite the incident wave at this part of the string using an oscillator, then what happens with the time advances, this incident wave and that reflected wave will basically going to do superimposition. Okay, when they superimpose, or when when we apply the principle of superposition, then a standing wave pattern will generate. Okay, so how this wave pattern will basically look like? As I told you that in standing wave, the position of the maximum and minimum of the wave will not change with time. Okay, so suppose at one instant of time, the standing wave pattern is like this. Okay, so say this is standing wave pattern. Suppose we assume like this is a standing wave pattern. Now these are the position of maximum, minimum, maximum, minimum, minimum, and these are the this is the position of minimum. Okay, so this position of maximum and minimum will not change as the time advances. That's why they are known as the standing wave. So say at time t is equal to t1, this is the standing wave pattern which we observe. Okay, so at another time, say at t is equal to t1, what will happen? The wave pattern will look something like that. You see, the position of maximum and minimum will not change, but their amplitude may differ. The position only will remain fixed, but the amplitude of the maximum and minimum will change with time. Okay, so if I plot it, then at time at instant t is equal to say t2, the standing wave pattern maybe look like this. Okay, you see there is a change in the position. Okay. Sorry, it will be sorry. I forget this purple line. Let's do it with the red line. So okay, So this is the position at time t is equal to t2. So at time t is equal to t3, again their amplitude will decrease further. Say it will become something like that, and at time t is equal to t4, what will happen? T is equal to t4, the maxima and minima, let's get shifted. Okay, so something it will be like that. Okay, so at time t is equal to t4, at time t is equal to t5, it will be something like that. Okay, at time t is equal to t6, again it reaches its maximum amplitude. If the maximum amplitude say a, so at time t is equal to t6, it reaches again the maximum amplitude. Okay, so you see the position of maximum and minimum, it's get shifted, but their the position of maxima and minima, they may changes periodically, but this point, the position where one point become maxima, at other point it will become minimum. Okay, so this thing may happen, but this position of extremum, they are not going to changes with time. Okay, so what will happen, what you will observe in real time will something like a envelope like this. This thing probably you have noticed when both end of the string is fixed and you just vibrate the string, then at one instant of time you may see such kind of an envelope. Okay, this envelope is nothing but the standing wave pattern. Standing wave pattern. Mind you, the incident and reflected wave, all the time they are traveling. Okay, so this wave will travel all the time, their maxima and minima will x shifted with respect to time, but the position of maxima and minima of a standing wave will not change with respect to x coordinate. Okay, their point, the position of their extremum will be fixed. Okay, that's why they are known as the standing wave. And when you observe for a the duration of certain duration of time, what you may observe is such kind of an envelope generation on the string. Okay, and in this envelope, in this way, with respect to time, this pattern will change. Okay, and this thing changes so quickly that only what you in real life what you will see is kind of a standing wave. I will put a simulation video on this with this lecture, with this part of the lecture. There you can easily see or easily learn how to simulate this kind of generation of a standing wave on the on the string when both end of the string is kept fixed. Okay, so this is basically what we mean physically, what we mean physically by the standing wave formation. Okay, in the other next part of the video, I am going to discuss about the mathematics involved in the formation of standing wave, and what the mathematics suggests about this picture which I have already depicted. Okay, so we are basically now going to do the analytical treatment of the standing wave formation. Okay, so for that we have to take two waves. One is the incident wave. Say y incident is equal to a, amplitude is a, exponential I omega t minus kx. This is in the positive x direction. So y reflected wave will be, amplitude is becomes if you remember, a1 is equal to minus b1, so it will be basically a exponential I omega t plus kx because it is moving in the negative x direction. So what we have to do, we have to superimpose these two oscillation to get the resultant oscillation, yi plus yr. So this is a e to the power I omega t minus kx plus minus a e to the power I omega t plus kx, right? So what we are going to do, we are going to take a e to the power I omega t as common factor. So basically it will give us e to the power minus I kx minus e to the power plus I kx, right? we can write it as a sine function. For that, what we have to do, minus twice a e to the power I omega t. Then if we do 2i, since we are putting minus here, so this term will take the first place, I kx minus e to the power minus I kx. Okay, so this term is nothing but the sine term, because if you remember, e to the power I theta minus e to the power minus I theta divided by twice I is nothing but sine theta, right? This you probably would have known from your mathematics class. So this will give us twice a e to the power I omega t. So this value will give us basically sine k into x. Okay, so this is the resultant amplitude of the standing wave. Okay, so now what we have to do, we have to take the real part of it. So it will so there is a twice I, sorry, there is a twice I here, 2 into I, because 2i will get cancelled out. So 2i into a, so e to the power I omega t is equal to cos omega t plus I sine omega t into sine kx. Okay, so this will basically give us minus twice ia cos omega t sine kx. I square is equal to minus 1, so basically this is twice a sine omega t into sine kx. Okay, so for real amplitude, we know that standing wave are real, therefore we have to take the real resultant amplitude. So real part of y is equal to twice a sine omega t into sine kx. Okay, so this is the resultant displacement of a standing wave. So standing wave, basically we are going to determine from this equation. Okay, now let's see what this sine omega t and sine kx term will do in case of a standing wave. So for that, let's come to this picture. We know the amplitude is twice a sine omega t into sine kx. Okay, so this term sine kx will determine the position of maximum and minimum, that is the extremum of the standing wave, and these positions are known as the nodes. Okay, and the position where the amplitude resultant displacement becomes 0, for example this point, this point, this point, this point, these are known as the antinode. Okay, these points are known as the antinode. Okay, so sine kx, this term will basically give us the position of this node and antinode, where the amplitude become maximum and where the amplitude become minimum. And this term sine omega t, what it will give us, how this position of maximum and minimum or how the position of extremum changes with time. As I have told you, the amplitude, the position of extremum will also have a periodic nature. So it will basically come to this minimum point, then again it will reach the 0.0 displacement, and again it reach the minimum minimum at that point, right? And after that it will again repeat itself to that extremum point. So this movement will basically governed by that sine omega t term, and the frequency of this movement will be governed by sine omega t term, and the fixed point of maximum and minimum, that will be governed by this sine kx term. Okay, so these two have real physical meaning. Sine kx will determine our point of maximum or minimum or extremum or 0 point. In this case, these are extremum and these are 0 displacement. So extremum and 0 displacement point will govern by sine kx term, and sine omega t term will show us at what frequency the minimum become maximum and maximum become minimum, because these two will happen periodically. Okay, and this will happen so fast that your eye can only see an envelope, because if we oscillate with a high frequency, our eye cannot detect such kind of formation. So our eye can only detect this kind of envelope generation, which will be clear from the simulation picture, which I will attach with this video. Okay, so basically this is the displacement, and this is the physical meaning of each term which is present in the resultant displacement, right? So I'm going to now I'm going to find where are the position of maximum and minimum, that is the extremum, and where are the position of zero displacement. Okay, these are the point of zero displacement, that is the antinode. Okay, so we can take to call it as antinode. Okay, so let's find out the position. Okay, it's very easy. We know resultant displacement, y is equal to twice a sine kx sine into omega t. Okay, we are going to find out the position, therefore we are going to use this factor. Okay, so y will be 0, the displacement will be 0 when sine kx is equal to 0. Okay, and sine kx will be equal to 0 when its value is equal to n pi, where n can be equal to n is equal to 0, sine 0 0, and sine 1 pi, sine pi is equal to 0, sine 2 pi is equal to 0, sine 3 pi is equal to 0, something like that. Okay, so kx should be equal to n pi. Okay, so kx we can express it with respect to wavelength. If the wavelength of the standing wave is lambda, then twice pi over lambda x is equal to n into pi. So pi get cancelled out. So x is equal to n lambda divided by 2. Okay, so position of this minima will be equal to x is equal to 0, then lambda by 2, then n is equal to 1, then n is equal to 2, it will be equal to lambda, then n is equal to 3, it will be equal to 3 lambda by 2. So these are the position of the minimum. Okay, so x is equal to 0, lambda by 2, lambda, these are the position of minimum. Okay, and when say kx is equal to and when we'll get the maximum displacement, this is for minimum, right? So this is zero displacement, not minimum, that's a zero displacement. And extremum point, extremum means this sine kx has to be plus minus 1, because the whole range of sine is between +1 and -1. So sine kx is equal to plus minus 1. So that value gives sine, we know it will be equal to n pi over 2. Okay, where n is equal to 1, n is equal to 3, n is equal to 5, ... Because you see, when n is equal to 1, sine pi by 2 is equal to +1. Okay, when n is equal to 3, sine 3 pi by 2, it is equal to -1. So extremum, this is maximum, this is minimum. So these are the position of the minimum. Extremum. Okay, so we can write now the kx is equal to n pi by 2, and k is equal to, as always, twice pi divided by lambda into x is equal to n pi divided by 2. Okay, so this thing get cancel out, then x is equal to n lambda. Okay, x will be equal to n lambda divided by 2 will come down here, so n lambda divided by 4. Okay, so for n is equal to 1, x is equal to lambda by 4. Okay, n is equal to 3, x is equal to 3 lambda by 4, ... Okay, so now a very interesting thing will come. So when you say, when n is equal to 1, how many minimum we will get? You see, when n is equal to 1, then 0 and lambda 2, here we will get some minimum. Okay, suppose a string, the both end of the string is fixed, therefore this point and this point, the displacement will be 0, because these 2 points are fixed point. Okay, so say the length of the string is like that, L is equal to lambda by 2. If the length of the string is like that, L is equal to lambda by 2, that means if both end of the string is fixed, this is x is equal to 0 and this is x is equal to lambda by 2, and this correspond to n is equal to 1. Okay, now you see, when n is equal to 1, in this case the position of extrema is equal to 1. the position of extrema for n is equal to 1 is equal to lambda by 4. So between these two, say this is lambda by 4. So lambda by 4. Okay. So what we will get? We will get this kind of a vibration. When n is equal to 1, the string will basically going to vibrate like this. Okay. So this vibration is known as the first harmonic. First harmonic of the string. Okay. Let me repeat it again. Okay. You see, first we are considering for n is equal to 1. Okay. When n is equal to 1, then there could be two minimum. Because before n is equal to 1, we have n is equal to 0 here. Therefore, these two minimum will be 0 and lambda by 2. Okay. Then we take a string of length lambda by 2. Then this point and this point will be fixed point. Okay. So these are the position of antinodes, say antinode. And between these two antinodes, how many nodes will be possible? Node means maximum displacement. That maximum displacement when n is equal to 1, its value, the position of the maximum displacement will be lambda by 4. So between these two, lambda by 4 is exactly in the midpoint between these two fixed point. Okay. So this will be the point of maximum and this will be the point of minimum. Okay. If the string vibrate like this, because this is a standing wave. Okay. And if the string vibrate like this, then this is known as the first harmonic of the string. That means string is vibrating in its first harmonic. Okay. Now let's take n is equal to 2. N is equal to 2. So in this case, how many minimum are possible? N is equal to 2. That means 2 lambda. So so there are 3 points where the amplitude will become 0. So that is 0, lambda by 2 and lambda. Suppose we are taking a string of length L is equal to lambda. So there will be 3 points where the vibration will gives us 0 amplitude, and that value will be equal to, say, this is 0 and this is lambda and this is how much? Lambda by 2. Okay. And when n is equal to 2, how many maximum are possible? There are two extremum are possible, lambda by 4 and 3 lambda by 4. Okay. If lambda by 4 is positive or plus 1, then 3 lambda by 4 will be negative or minus 1. So this point correspond to lambda by 4 and this point will correspond to 3 lambda by 4. So what we are basically going to see, we are going to see this kind of a vibration. Okay. And at one instant you are going to see this kind of vibration in the string. Okay. And this is known as n is equal to 2 vibration, or this is known as the second harmonic of the vibration, second harmonic of the string. Okay. Similarly, we can proceed to n is equal to this is n is equal to 2, right? Similarly, we can proceed to n is equal to 3. For n is equal to 3, you have to take a string of length 3 lambda over 2, because this is that value, and 0 and 3 lambda by 2 will be fixed. So we are basically going to have 4 point of 0 vibration. That is, and on this axis we will get 4 point, and between these 2 points you are going to get 3 extremum cases. Okay. So if I plot it, that it will be something like this. So here we have a 0, and here we have 0, and here we have what is the value? As you can see here, this is 3 lambda by 2. 3 lambda by 2, and between this we have 2 minimum, and these 2 minimum are at what? Lambda by 2 and lambda. So if it is lambda by 2, then this will be equal to lambda. Okay. And in between them there will be 3 maximum or extremum. So first extremum will be at what point? At lambda by 4. Okay. So you put lambda by 4 here, and second will be, as you can see, 3 lambda by 4. It will be exactly midway between these 2 points, 3 lambda by 4, and in between these two there will be another extremum. Okay. So the vibration will be something like this. Okay. So if I plot this figure also, because one maximum will become minimum at some time. Okay. So it will be something like this. Okay. So this is known as the third harmonic. how many notes are there? 1, 2, 3. Okay, the third harmonics have how many notes? 3 notes. Okay, harmonic anti notes are there 1, 2, 3, 4. So it will have 4 anti notes. Okay, so this is true for any order of harmonic. So nth order of harmonic, we can have n notes, and how many anti note? N plus 1 anti note. So this rule will basically apply for this whole harmonic generation. Okay, so if you hit the string with the appropriate frequency, then you can observe such kind of harmonics generation on the string. Okay, for that you have to choose a particular frequency, and that is known as the frequency of harmonics. You have to oscillate that end of the string with this particular frequency, that is the frequency of harmonic, and then what you can see is the excitation of such kind of a nth harmonic standing wave on the string. It is a very cool practice to do in real life. Even if you can try at home, just fix two end of the string and try to vibrate the string and try to excite such kind of harmonic oscillation in that string, and with little bit of luck you can observe up to 12 order of harmonic generation on a ordinary string. Okay, this is a very exciting and beautiful experiment to do at home. You can basically do it at home also. Okay, so the next part I'm going to discuss a little bit about the frequency of harmonics, and then we will proceed through the energy of such kind of standing wave pattern on the string. Okay, so thanks for your attention. Good morning, student. There was little mistake in this part of this video. In the part of the video, I have termed the point of maximum or minimum amplitude as the node, and the point of zero displacement as the antinode, but it should be opposite, the point of maximum and minimum displacement. So this is the point of maximum displacement, this is the point of minimum displacement. These are actually antinodes, and where the two end of the string are fixed, where the displacement is 0, because these two end are fixed, and also this point and this point, these are termed as node. It should not be antinode. In this part of the video, I have termed it by mistake as antinode, but it should be actually node. Okay, so for this kind of third harmonic generation, as you can see, there are how many nodes will be there? 1, 2, 3, 4. So this 4 should be node, and there how many antinodes should be there? There should be 1, 2, 3. 3 antinodes should be there. So this is not node, this is antinode. Okay, so for nth harmonic generation, there will be n plus 1 node and n antinode. Okay, n antinode. So this was a little mistake in this part of the video, and sometime I termed in the video in 2 or 3 places the point of zero displacement as a minimum displacement, but be quite sure that when you see this kind of point, these are the point of zero displacement, not the minimum or maximum displacement. Maximum displacement is this part, and minimum displacement is this point. Okay, and this all the other point on the x-axis, these are the points of zero displacement. Okay, so I hope you will get clarified about the mistake which I have done in this part of the video, and I hope you will correct it according to this statement. Okay, so thank you.